All right. Hi, you guys. I hope you're doing well. I'm going to try to talk loud enough because this microphone is really dumb right now. I need to go buy myself a new headset. All right, let's present this guy so we can all see it. Nope, I don't want to go to end of the slide, so I want to go to the beginning. Really? All right, there we go. All right. I hope you guys are having a great day. I hope the quiz was reasonable yesterday. I haven't got them graded yet. I'm going to work on grading those today and then getting some other grades input into the grade book as well. So you guys kind of know where you're at. We only have a few weeks left as we head into, I think we only have like 5 weeks maybe. Um, which I have to say, I am ready for summer after all this craziness over the past 6 weeks. Um, all right, so today we're going to have our next stoichiometry lesson. We're going to be talking about excess reactants. I'm hoping that at the end you'll be able to calculate the limiting reactant, which we did in our last lesson. So that part will be review. And then I want you to calculate how much of the excess reactant reacts and how much is left over. Um, and so when we calculate our limiting reactants, remember there was the larger amount is what we call the excess reactant. And today we're going to add one more step in order to be able to calculate how much of that was actually used and how much is actually left over. So, all right, let's just get going. We're going to do a limiting reactant calculation to start off. Um, so our example, how many moles of iron oxide can be produced from the reaction of 13.17 moles of iron with 18.19 moles of oxygen? So our knowns, we know we have 13.17 moles of iron, we know we have 18.19 moles of oxygen, and we know that iron oxide is our product. So we can go ahead and write out our equation. We have iron and oxygen creating iron oxide, okay? And we're going to put that into a formula. Remember, oxygen is a diatomic element, so we have two of those two of those atoms in a molecule. And then our iron, it tells us, thankfully for our Roman numeral, right, that it's iron 3 oxide. So you would know that's a +3 charge on the iron. We know that oxygen has a -2 charge. So when those ionically bond, we have to have 2 iron atoms for every 3 oxygen atoms. That's what that molecule would be. Now, as you guys move forward, you will start to have some of these memorized. Like this reaction, you're going to always know it's iron 3 oxide. We've used this reaction multiple times up to this year, but okay, so now we need to balance out our equation. I'm going to add a few coefficients in here. So we have the same numbers of atoms on each side. So now we have 4 iron atoms in our our reactants. We've got 3 oxygen molecules in our reactants, and then we have 2 um, iron oxide molecules in our products. Now remember, these are also our moles, right? So really we have 4 moles of iron. We have 3 moles of oxygen, and we're producing 2 moles of iron oxide. All right, so now we have our equation. We're ready to go. We can start doing some calculations. Um, our question asks us how many moles of iron 3 oxide can be produced from the reaction of 13.17 moles of iron with 18.19 moles of oxygen. So we're going to be looking at these relationships. We're looking at our iron to iron oxide and our oxygen to iron oxide. We're going to start with the iron. So it gave us 13.17 moles in our problem. Now, it's already in moles. Yay! So we don't have any weird extra steps we have to do. We just simply have to use our mole ratio. So we're going to plug in our mole ratio. Sorry. So there's 2 moles of iron oxide produced for every 4 moles of iron that react. So we can cross that out. We would figure out we are using 6.585 moles, or we're producing 6.585 moles of iron oxide when we use our 13.17 moles of iron. Okay, now we got to look at how many moles would be produced with starting with 18.19 moles of oxygen. So we're going to start with that. Plug in that mole ratio. It's a 3-to-2 ratio. So for every 3 moles of oxygen that react, we should produce 2 moles of iron oxide. Cross that out, do the math, and we would produce 12.13 moles of iron oxide. So we can go ahead and cross that one off. We know that the limiting reactant, because this is the smaller number right here, The limiting reactant is our iron. All right, so that's just a review of limiting reactants. Um, Hopefully that was helpful. And now we're going to actually look at our excess reactant, which in this problem, our excess reactant is going to be our O2. So we should have, after doing this, remember the iron was all used up. When we produce this amount, this is the most that can be produced, okay, is the 6.585 moles of iron oxide given these amounts at the beginning. So we should have had some excess excess oxygen, all right? So we're going to do another problem now and talk about our excess reactant, okay? There's going to be two parts to this. Our first problem, our first part is going to be A, which is what mass of cobalt chloride is produced from the reaction of 3.478 times 10 to the 23 atoms of cobalt with 57.92 liters of chlorine gas at STP. So that'll be our first part. And then the second part, we're going to look at how much of the excess reactant reacts and how much is left over. So this is going to take multiple slides. If you need to pull up your PowerPoint, like print it off so you can walk through these, I would suggest doing that, or do this problem all on one page. These are longer problems. You have multiple calculations, all right? So we're going to start with our equation. We have 2 moles of cobalt, 3 moles of chlorine that react and produce 2 moles of cobalt chloride. So our first question, what mass of cobalt chloride is formed? So let's go ahead and start with our 3.478 times 10 to the 23rd atoms of cobalt. We can go ahead and convert this to moles using Avogadro's number. All right, we're going to cross those off. Now we're in moles of cobalt. We can look at our mole ratio of cobalt to cobalt chloride. So it's a 2-to-2 ratio. And then we need to come up with our molar mass of cobalt chloride so we can figure out how much is produced. And so we just pop that in, 165.13 grams. If you look up here in our cobalt chloride, we have 1 atom of cobalt for 3 atoms of chlorine. So you just add those up and we'll get the molar mass. Okay, so we would produce 95.40 grams of cobalt chloride if we start with 3.478 times 10 to the 23rd atoms of cobalt. All right, now we're going to look at our chlorine gas, all right, and we're starting with 57.92 liters of chlorine gas. We're going to use our conversion factor that 1 mole equals 22.4 liters of a gas at STP, and we have it at STP, so that's nice and simple, and we can cross that out. So now we're in moles of chlorine. Okay, we're going to use this ratio, our 3-to-2. We have 3 moles of chlorine used to produce 2 moles of cobalt chloride. So we'll put that in, cross those out. We have to grab our molar mass again to turn it into grams. Okay, so if we start with 57.92 liters of chlorine gas, we would produce 284.7 grams of the cobalt chloride. We can go ahead and cross that off. That is clearly larger than the 95.40 grams of cobalt chloride. So our limiting reactant then is our cobalt atoms. And the most that can be produced is the 95.40 grams. So now, okay, we're going to do something else. The limiting reactant is the chloride. The excess reactant is the chlorine. So, or cobalt, sorry. Cobalt limiting reactant, chlorine excess reactant. Okay, so now we have to do another thing. All right, so we have to figure out how much excess reactant is actually going to be used. And we're going to use our ratio of our reactants to do this one, okay? To find out how much excess reactant reacts, do a third calculation using the limiting reactant as the known and the excess reactant as the unknown. So if we're given 3.478 times 10 to the 23rd atoms of cobalt, okay, we're going to grab the molar mass, we're just going to use Avogadro's number and turn that into moles. Then we're going to use this mole ratio of our limiting reactant to excess reactant right here. So we have 3 moles of chlorine used with 2 moles of cobalt. Okay. We're going to grab our 22.4 liters to convert that. So we're actually going to use 19.41 liters of chlorine, okay? If we're given this much cobalt, that is how much chlorine is going to be used as well. That needs to react with the cobalt. So this is the amount that when you're given the 3.478 times 10 to the 23rd atoms of cobalt, this is how much chlorine is going to react with that, okay? So what we can do is we can take we're trying to figure out our excess reactant, right? So we can take our original 57.92 liters of chlorine gas, and we can subtract the 19.41 liters that's actually going to be used, right? And then we would get that there should be an excess of 38.51 liters of chlorine gas. Okay? So that is the amount that is left over, predicted to be left over. All right. If you guys have any questions, go ahead and send me a text or email me. If you want to set up a Zoom to go through this individually, I can. I will be posting a video later today going through one of the problems on your homework worksheet. So be looking for that. And I'm going to try to do that hopefully fairly soon so that that'll get posted as well. But you guys will be able to see an example, just another example. It's always good to go through several examples. I hope you all have a great day. I'm going to be catching up on grading today. If you have any further questions, like I said, just let me know. And yeah, I hope you guys have an awesome day.